Okay, welcome to Physics 209. Let's go get started with today's discussion. All right. So, before we begin, let's talk about science. All right. So, what is science? All right. Well, you can think of it as a body of knowledge organized in a very specific and rational way. Knowledge organized in a specific and rational way. Okay. And there are basically two legs on which science stands on. One is theory. Okay. And one is experiment. And what theory does, theories are models of the world. And experiments are observations tests and experiments. Right? So, or measurements, actually, more precise is measurements. Right, so this part is the real world. This part is our model of the real world. Okay, and there are these two things are related to each other. So theory make predictions, right, about the outcome of experiments, and experiments provide data that goes back in to try to create these models, right? And data could be a confirmation, or refutation of theory, right? Okay. So the main thing about science, right, is that this is the key, to be able to make predictions. So, okay. Okay. So the science is testable. Testable. Okay. And so without this test, there is no science. Okay. So the caveat here, right, is that all science is wrong at some level. Okay? Like science is not a complete understanding of the entire universe, but correct in others. Right? So for instance, like we don't completely understand quantum mechanics. Quantum mechanics cannot be the explanation of the entire universe, right? But that doesn't prevent us from basically building stuff like iPhones or or smartphones or computers or whatnot. Okay. All right. So in this class, let me make sure I can get through this thing. In this class, this is this class is 209, 210, right? We will discuss classical physics. Right? So this is basically physics of quote unquote large bodies that don't go too fast, right? So this is like solids, solid bodies, fluids, motion, electricity, magnetism, okay, etc. All right, so large is basically will be apparent if you continue in physics. What large means basically means bodies are not subject to quantum mechanical effects, and fast means basically it's not approaching something like the speed of light. Okay. Alrighty then. So okay. So physics is experimentally driven. Right? So by and large, most of the stuff we know about physics is first basically deduced or observed in experiments. So that means observations and measurements. Okay, so what do we measure? All right, let's go think about this. Okay, so let's go list some things we measure. We measure how long someone is, the length, height, width, those are the things, right? We can measure time. We can measure how much material something has. This is the mass. We can measure basically how strongly something pushes, force. Right? We can measure how quickly something moves, the speed, or more precisely, the velocity. Okay? We can measure how quickly these speeds change, acceleration. Right? And finally, we can measure maybe how much things takes up, right, volume. Right? And of course, there might be others as well. Right? Okay. Now, it turns out, right, that you can express all these other things in terms of these three quantities to start with, right? So these three quantities constitute what's called the base units. Oops. Okay, and all quantities can be expressed in base units. Okay. Right. So for instance, right, let's consider something like speed. Okay? What is speed? There's an example here. Okay? Well, speed is basically how far you go in a certain unit of time. So it's basically some length divided by time. Right? It's distance over time. And guess what? Basically, so therefore, if you use a unit for length, unit for time, like let's say this is an inch or foot or meter or mile or something like that, and time, second, minute, hours, something like that, you can devote a speed, right? So that's why, for instance, like how fast you can drive a highway, like 60, 70 miles an hour, 60 miles per hour, right? Length over time. All right, so now that's great. All right, so if we come up with basically a few base units, we can measure. We can also determine what all the other quantities are. All right. So how do we determine base units? Okay. Now, because we're in the United States, we have to be special, all right? But everyone else, basically, and in this class, we will use a system called Système International. Okay, or SI units for short. Okay, right, for mass. Okay, because that's one thing we care about. For time, another base unit we care about, and for length. And for mass, we're going to use the kilogram. For time, we'll use the second. And for length, we'll use the meter. Right? Okay. So these are actually very useful because they were thought of basically much more systematically than most of the units we think about, right? And so as a result, it's actually quite useful, right? Okay. Now, I will also use well, I'll start a new page on this one. Okay, so the SI units here. Okay. I also use an alternative system and actually it's basically my work actually called CGS. All right, so what's CGS? CGS is pretty easy. It's basically means it's mass, length, time. Okay, so let's do that right. Yeah. Okay, so the mass, I'm going to use grams instead of kilograms. For length, I use centimeters instead of meters. And for time, I use seconds. All right? That's why the CGS comes from. CGS. Right? Okay. In astrophysics, these are known as God's units because certain calculations are just way easier with them, basically. If you use SI units in astrophysics, there are these constants that pop up. Basically, you got to remember. But with CGS, the constants just go away. Not to worry about that at all. Okay? But for the most part, basically, when we do introductory physics, we mainly use SI units. Okay. When we measure something, so fine. Okay. So we have a unit. When we measure something, okay. Okay, we have two parts. Okay, so we give it a number or value. Okay. And a unit, right? So basically, the units basically give the measured quantity something called dimension, right? These units have a quantity or quality, I should say quality, known as dimension. And basically, dimension is essentially the association of the physical thing that you're measuring with. So for instance, if you say like something is 2 meters, right? 2 is the number value, meters is a unit, but unit has a dimension. What's that dimension? It's what meters is measuring, length, for instance, all right? Okay? So there's no quantity that expresses the unit in terms of base units. Okay? So for instance, okay, length has dimension of length. Okay? Or you could say this is some L. Okay? Time has dimension of time. Or you could think of this as capital T. Okay? This is a bracket means dimension. So mass has dimension of mass, or capital M. Okay? Right. Okay, so then basically, let's take quantity like speed. So then I'll say speed has dimension of what? Well, it's length. Whoops. Length over time, or this is just going to be L over T, right? Okay. You can do other things as well. For instance, area. Area is a length times width or something like that, right? So this has dimensions of basically length. Well, I'll try this. Length times length, which is just L times L, which is just L squared, right? Okay, so this is really useful, actually, it turns out, right? Because, okay, so looking at base units to get other physical quantities is known as what's called dimensional analysis. Right? Okay. So basically, you just mix and match these things to see how you can construct one thing from other things. All right. Okay, so let's give it a few examples of this, and then we'll do a rather complicated example of this. All right. Let me see if I have stuff here. Okay, so let's try this, right? Okay, so to give some examples of dimensional analysis, all right, let's suppose, okay, so let's suppose the example, you have a car moves at, let's say, 60 meters per second for 10 seconds. All right, how far does it go? So you might know this, right? So basically, you might know the distance is equal to velocity times time. All right, so you might know that already, okay? But if you didn't, you can figure this out, right? Okay. Use dimensional analysis. Okay. So let's do this, right? So we can do the distance. Well, with distance, something we want. This has units of length, all right? This is what I want. Okay. The velocity is something I'm given, right? This has units of length over time. Okay. And I'm given a t, which is time. Okay. All right. So how do I get this from these two things? Well, one thing I guess is I could write basically L, which is d. Well, this might just be equal to, has to be some product of something like this, length over time, all right, this is v, times t, right? And so from this, looking at this, in order to get length out, I have to basically take something that has length over time, multiply times time, and I'll get length. So that means velocity is distance times time, right? And that would be correct, okay? Okay. Now let's do one more complicated example, right? Okay. And the more complicated is as follows, all right? So suppose I tell you that you have a mass of 60 kilograms and a speed of 5 meters per second. Okay, I'm gonna ask, what's your energy? Right now, this kind of doesn't make any sense because energy has many different forms, right? And what it really speaks to me is they're kinetic energy, right? And you have no idea what energy is yet, okay? But I will tell you one thing. The units of energy, say the unit of energy is going to be something like this. It's going to be basically mass, length squared over time squared, okay? So I have all this stuff. I have a mass here, or some given, so I want energy, which is units of basically mass, length squared over time squared. Okay? And what I have is I have mass M, so I'll call this E, which has units of mass. Right? That's my 60 kilograms. And I have a V, which is units of length over time, say for instance. All right, so how do I get this thing? So I want to get mass length squared time squared, so this is energy. This is equal to, well, I have a mass here, so I guess there's an end here somewhere. Okay? And now I have length squared time squared. So the only way to do that is I multiply V twice. So then I'll just do L over T entire thing squared, and this will give me this, right? So I assume that the form is of this form, E equals mv squared, and that would be wrong. Okay, it's wrong because the actual answer is E is equal to 1/2 mv squared. Now, there's no way to get the 1/2 from dimensional analysis, but you get the general form of it correct from dimensional analysis, right? And that's the key, basically. You just get some idea of what it needs to look like, okay? So no matter what, I know that if I compute the energy, something like this must appear somewhere in the equation, right? I can't get the constant out front, right? But I can get basically the general form, right? Okay. So those are a few things related to dimensional analysis, right? Okay. So, let's see. Okay, let's talk a little bit about significant digits. Let me just see here. Right. Okay. All right. So when we make measurements, right, the level of precision can vary by quite a bit. Right? Okay, so let's measure length. Okay, and suppose you measure basically some L is equal to 1.503 meters, right? Measuring basically someone's height, for instance. Okay. All right, actually, measure length of a table. Okay. Now you are taking care to do this. So you're doing this really well. Okay. You get your measuring stick. You measure really well. Okay. Now on the other hand, let's say you have a lab partner. Okay, so your careless lab partner. Okay, who's definitely not as careful, all right? Okay. They measure the width. One meter. Okay, that's what they measure, right? Okay, so suppose now I ask, what is the distance around the table? Okay, so it's the perimeter of the table. So, okay, so you're measuring, this is some table here. L, W, and you did this side, your partner did the other side. Partner's not very careful about it, right? And so you get basically that the perimeter is going to be 2 times the length plus 2 times the width, right? So it's this one, this one, this one, this one, adding all the way around, okay? Right? So, what's the level of precision you can arrive at? Okay, so this is the level of precision. It's 1 meter. That's the level of precision they have, right? So, when adding, right, or let me just make sure it's precise, or subtracting, keep only up to smallest of decimal places. Right? So for instance, if I do this, 2 times the length, right? 3.006 plus 2 times the width, 2, okay? Then I basically get 5 meters. And that's it, that's my level of precision, okay? I worked it all this extra work, so this is basically extra work. Wasted, right? But that's just life, okay? Because you're governed by the level of precision which you measure the width at. And because your partner is just not very careful, that's basically the weakest chain here, right? Okay. So what about the area? Okay. The area is equal to the length times the width in this case. Right? So in this case, this would be basically 1.5003 times 1, right? So in multiplying and dividing, you can only keep smallest number of significant digits. Okay, so here I kept the smallest decimal point, right? It's up to here. Okay, here I have to keep the smallest number of significant, which is actually just 1 here. So let's multiply this out. This is 1.503. And so basically I only keep up to here. Maybe I round this thing up. 2 meters squared. Okay, that's the number. That's the level of precision that I can have now, right? Which is terrible, right? Because you worked really hard to get this extra precision, and now you lost of it because your partner's not able to do it correctly. But that's life, right? We've been down those paths before. Okay. All right. So it is important to keep track of significant digits. Right? So let's consider these following numbers. So 0.1, okay, 0.10, 1, 1.0, 10, 10 dot, and 100, okay? So how many significant digits in each, right? Okay, so this one I can count, right? This is just basically 1 significant digit, so that's basically 1 number of significant digits. It's 1. This one has a point, right? 1 and then 0, so I'm measuring up to this point. This is 2. This has 1 significant digit. This has, I have a point and a 0, 2, right? Let's skip this one for a second. This one has basically points, that means the 0 is precise, that's 2 again, right? So what about this one, this one? How many significant digits do they have? Turns out that only has one each, right? And you might wonder, like, well, what do you mean by that? It's like, I thought this is 10, this is 100, right? Shouldn't there be 3? There's no decimal place there. The decimal place doesn't mean, if there's no decimal place, there's no way of expressing that this is correct. Now, this one actually is a question mark in particular, because the thing is, like, you have no idea if this one is significant or not. There's ambiguity here, all right? Okay? So, how do we figure this out? Okay? So the only way of doing this, there's no way to fix this in the regular numbers, right? The only way of fixing this is to express it in scientific notation. Okay? Right? So this could be 1 or 2. Okay? So that's what makes it annoying. Okay? So we can fix this with scientific notation. All right. So let's talk about how we can do that. Okay. So so any number can be expressed in scientific notation as, okay, so there's some things here times 10 to the y. Okay, so this is some integer power. And this is the number of significant digits. Okay. So for instance, I have 0.01. This is equal to 1 point times 10 to the minus 2, right? Okay. 0.010, that's 1.0 times 10 to the minus 2, right? So this has one significant digit here, that has two significant digits there, okay? And then for 100, which is the problem that created this issue in the first place, this is either 1 point times 10 to the minus 2, in which case it's just one single digit, or 1.0 times 10 to the 2. In this case, there are two single digits. So now its ambiguity is removed now. Okay? And multiplying is pretty easy in scientific notation. So is dividing, actually. Right? In this case, 3.0 times 10 to the minus 1 times 4.123 times 10 to the 4. What is that equal to? So just multiply everything out, right? And you keep in mind that there's two single digits. So basically, this is 1.2, so 3 times 4 is 12, but then it's times, and you add these together, so it's 12 times 10 to the 3, which is 1.2 times 10 to the 3. I just keep the numbers in the digits there, right? So it's basically 2 here, because I'm taking the smallest number of digits I have, which is 2. Okay? Times 10 to the 4, sorry. Okay. Right. Now adding is much more complicated. You actually have to convert this back to decimal notation. So for adding and subtracting, this is convert back to decimals notation. All right. Excellent. Okay. So now let's talk a little bit about basically certain quantities in physics, right? Let's talk about vectors. All right. Okay. So, in physics, we have quantities, whoops, that are just numbers. These are called scalars, right? We also have quantities with both a number, magnitude, and direction. These are called vectors, right? Okay, right? So they're represented by an arrow. Okay. Okay, so as variables, we write vectors as x with a vector on top of it, with an arrow on top of it, and the magnitude of x as x. The absolute value thing actually converts it back to a magnitude, which is a scalar quantity. Okay. Now, see if I get this light on. Good. Like scalars, vectors can be added and subtracted. Okay? But it's a little different, okay? So for instance, suppose we want to construct the vector C, which is equal to vector A plus the vector B. I'll tell you that A is equal to something that looks like that, and B is equal to something that looks like that. Okay, where the length of the arrow indicates its magnitude. Okay. All right. So there are two ways of doing this. Okay. Okay. The first way, head to tail. Okay, so you have basically A and B. Okay, so you draw A here. You take the tail of B, you put it at the head of A. And then basically you draw from the tail of A to the head of B. This is the C vector there, right? Okay. There's another way of doing it, which is equivalent. It's the parallelogram method. Let's see if I can. Okay. You draw A like this, B is like that. And you just construct a parallelogram. Okay, so this one you take here, that one you take out there. This is B, this is A. And you draw from one end of the parallelogram to the other end of the parallelogram. And that's C. Okay. Alrighty. Now, to subtract a vector, we want to basically just do add negative. Oh wait, hold on. My thing is broken now. Okay. Give me a second. While I pause this thing here. Okay, so I think I'm still recording, right? So hopefully this works. Right. To subtract a vector, okay, add its negative, right? So A minus B, that's just A plus minus B, right? So if B is going this way, that's B, then minus B, same length, just reverse the direction, right? And so if I want to construct this thing, then in that case, that's just going to be A is something that's like this, there's A, okay, and then that's minus B, right? And then basically, let's see right there, using the head to tail method, right? Right? Okay, we can also multiply vectors by a scalar, right? So this is 2A, oh, sorry, this is A, then 2A is just this A plus A, you can go that way, 2A vector, okay. Okay, so there's only so much you can do with drawing vectors, right? Okay, so to work with numbers, right, we need a coordinate basis. Okay, which consists of unit vectors, right? So basically having magnitude 1, right, that are orthogonal to each other set at right angles. Okay. Okay. So the usual basis that we use is x, y, z, right? We're measuring length with height, okay? And consists of unit vectors I hat, j hat, k hat. So this hat part, that just means they're unit vectors, right? Or you could write them as x hat, y hat, z hat. Your preference, really. I don't have any particular issue with it each. A lot of times we end up using x, I hat, j hat, k hat because x and y and z are used everywhere else. But at the same time, basically, these things are associated with some real x, y, z coordinates, which we learn and are familiar with. So there's not too much confusion between the two, but you can do whatever you like. All right. Okay, so let's draw this thing out. Okay. This might be the x-axis. This might be the y-axis. And then this would be the z-axis, right? And you can think of these as I hat, j hat, k hat. These are unit vectors to define it, basically, right? Okay. So any vector A can be expressed as a sum of these basis vectors, right? It's basically all the basis vectors are all the unit vectors that make up the basis, basically, right? So in particular, you could write A as equal to the magnitude in the x direction, magnitude in the y direction times the j hat, magnitude in z direction times k hat, right? Or if you don't like that, okay, doesn't really matter, right? As long as you don't get confused, basically, these are all the same unit vectors, right? So these objects here, right, are the components of the vector. Okay. Okay. Now these are useful, right? Because we can now do mathematical operations. Right, along each unit vector, along each basis vector. Right? Okay, so for instance, example, okay, C is equal to A plus B. Okay, if we express these in component form, this is AX I hat plus AY J hat plus AZ K hat plus BX I hat plus BY J hat plus BZ K hat. We just add them along, right? So this is basically AX plus BX I hat plus AY plus BY, J hat plus AZ plus BZ, K hat. Or in other words, this is CX, CY, CZ. Okay? And then likewise, basically, multiplication okay, C is equal to S times A. That implies that basically CX is equal to SAX, CY is SAY, CZ equals SAZ. Okay. All right. Let's try a few examples. Okay. All right. Let's let A is equal to 1 I hat plus 2 J hat plus 3 K hat. And then B is equal to 4 I hat plus 5 J hat plus 6 K hat. All right. C is equal to A plus B. Well, that's just easy now. Let's write everything out. 1 I hat plus 2 J hat plus 3 K hat plus, now let's do B, 4 I hat plus 5 J hat plus 6 K hat. And you just add them together. So 1 plus 4 is 5 I hat, 2 plus 5 is 7 J hat, plus 3 plus 6 is 9 K hat. Right? Okay. Right? Or you write a CX equals AX plus BX, CY equals AY plus BY, CZ equals AZ plus BZ, and in which case this is now just going to be 1 plus 5, 1 plus 4, 1 plus 4 is 5. This is 2 plus 5 is 7. And this is 3 plus 6 is 9. Okay? Okay. Now let's try. C is equal to A minus B, right? Well, that's just going to be equal to. So that implies, so what we have is that minus B is just reverse sign everything. Minus 4 I hat plus minus 5 J hat plus minus 6 K hat, right? And now you just basically add them together. C is equal to A plus minus B. That's just going to be equal to, let's just see, it says 1 minus 3 is minus 3 I hat minus 3 J hat minus 3 K hat. Okay. And finally, let's try one more last example. Multiplication by scalar. C is equal to 5 A vector. Well, that should be 5 times 1 I hat plus 2 J hat plus 3 K hat. 5 times 1 is 5 I hat times 2 is 10 J hat. 5 times 3 is 15 K hat. and that's it, right? And then we're done. Okay, so that's it for this week, and basically we'll continue it next time.